law of partial pressures. Okay, this is the same John Dalton that we talked about. He was the English scientist who had not even a high school education. He was a school teacher, and he came up with his atomic theory. Okay, thank you. This the same guy, and very intelligent. You know, the instrumentation there was not great, but the stuff he still used is still very, very, very important. Okay, Dalton's law of partial pressure. He had a few postulates to this. He would say gases are miscible if they do not react. Okay, so some gases react together. Okay, some gases react together. Like I was talking yesterday, I think in my Chem 2 class, talking about how acid rain made by water vapor and sulfur trioxide reacting in the air to make sulfuric acid. That's how you get acid rain. But not all gases react. Okay, we know carbon dioxide and oxygen don't react. So by saying that they're miscible, we're saying that they mix. Okay, that's just a fancy way of saying that they mix. Okay. Yeah. Now here's a thing. Okay, this is he's kind of think this idea of moles and pressure can be used very similar. What he's saying that Dalton's law says that the total pressure equals the sum of all the pressures. Okay, there's nothing else that's added. Okay, you know, that's not the same thing with money. All our total amount of money, we would add up all our money in here, wouldn't we? And we've got our total money. That's the same process with Dalton's law of partial pressures. Okay, all the individual pressures add up to equal the total pressure. All the individual pressures add up to the total pressure. Some of these problems are extremely straightforward and easy. Some you got to apply some other laws with them and do. Okay, so our examples, and let me switch out screens. So I didn't hit record. So my total pressure would equal the sum of all my pressures. Okay, so pressure O2 plus pressure CO2 plus pressure SO2. This could be different. Okay, this could be different depending on what things are present. There could be 2 things here. There could be 8 things here. There could be 20 things here. But if you're looking for the total pressure, you add them together. So 1.77 is O2, 0.895 is CO2, 0.33 is SO2. So what is your calculator answer is what, Nikiliana? 2.995. That's not my correct answer, though. That's my calculator answer, because when I'm doing this, I'm adding, subtracting, aren't I? So I need 2 decimals, because this has 2 decimals, this has 3 decimals, this has 2 decimals. So I need 2 decimals. So I don't necessarily round up. I round to the even number, so it would round to 3.00 ATM. Yep. Because I need 2 decimals. Now, I don't have an example for this one, but if I was given the total pressure and I was looking for the partial pressure, what would I do? If I was given the total, let's say I was given the total and I'm looking for CO2, what would I do? Subtract the total minus the O2 minus the SO2, okay? So if you're looking for something else, you subtract the total, then you subtract from the total the other things there, okay? So that problem, this part of this is extremely, extremely simple. Okay, our next example is, this is a long question. One is a little bit more difficult. Okay, you're giving pressure and volume in here. Okay, and this is kind of how all these words will be, all these questions like this will be worded. When you're talking about 2 different flasks. Okay, when you have 2 different flasks like this is still Dalton's law of partial pressure. Okay. But we know that this changes, okay? We know that this changes some things. This, Dalton's law of partial pressures, really affects like putting air in your tire, okay? You can air up your tire anytime, can't you? No. What? Well, that has nothing to do with that. Is now if the air tank has a lot of pressure in it, I can air up my tires, can't I? But I know if I have a small air tank with not much pressure, I'm not going to be able to put a lot of pressure into my tire, okay? Because when you put it on there, all you're doing, you still might have pressure in the tank, and your tire still might be flat. All that's doing is equalizing the pressure, okay? All that's doing is equalizing the pressure. So that's why sometimes your tire still might be flat. Now, if you have a generator air tank, it's going to be fine. But if you got a little air bomb, it might not work, okay? because you need because this is Dalton's law to go in there. That's why you see like commercial places have very big air compressors. Okay, their tank is very, very large. It has a very high volume and a very high pressure. Maybe at your house you have a small air tank. You can get a very high volume, very high pressure, but the volume will be smaller, so it can really restrict what you can air up. Okay, so when I have these things with these two flasks, this is code words for I need to do a Boyle's Law problem first. Okay. I've got to do I have two flasks, so I've got to do two problems first. So I'm going to split this up into flask A and flask B, okay? So over here, I'm going to have flask A. And over here, I'm going to have flask B. And I'm going to split these up, and I know these are going to be P1, V1, P2, V2 on both of these, okay? So I'm going to have to do two problems first. Oh, I made a mistake on that. So P1, V1, P2, V2 on each one of these. So it doesn't matter what flask you start with. We'll start with flask A. What is the initial pressure of flask A? 0.773. And that's in ATMs. Okay, and I don't have enough room to write ATMs in there. What is my initial pressure of, my initial volume of flask A? 2.00 liters. Now I'm going to skip over here to flask B. What's my initial pressure? 1.09. And what is my initial volume? 2.5. But I don't have enough information right now to solve these out, do I? I still have two variables on how I have it set up here. But I know something, though, don't I? What do I know? I know each individual volume, don't I? So if they are connected, won't I know my final volume also? So to find V2, all I do is add the V1s together. So the final volume would be 4.50. Because I have 2.0 liters in flask A. I have 2.5 liters in flask B. I connect them. My total volume now is 4.5. So they are both 4.5. In a problem like this, your V2s will always be the same number. Your V2s will always be the same number. If there were, I think on one of your homework problems, you have 3 flasks, okay? You have 3 flasks. So you would add the V1s from each of the 3 flasks together. Now, can I solve these out? Well, now I know that flask A's final pressure, because we know that as the volume gets bigger, the pressure is going to go down. Flask A's final pressure would work out as 0.773 times 2.00 equals X times 4.50. And then flask B would be equal to 1.09 times 2.50 equals X times 4.50.
What is flask A?
Flask A is points. I just plugged stuff in. 0.773 times 2 equals X times 0.450. Flask B being 1.09 times 2.50 equals X times 4.50. So flask A has a new pressure of, the P2 of flask A is now equal to, I need 3 significant figures, 0.344 ATM. Flask B is going to be equal to what? 0.666, 606. So by doing that, I have now answered the first question. Okay? The new pressures, the partial pressure of each gas is that. Okay, I've answered that question. So A is complete. Now, how would I do part B? I add the two numbers together. So part B, I ran out of room on this one. Part B would be the total pressure would equal flask A plus flask B, so it'd be 0.344 plus 0.606, and that equals 950. So when you have something like this, when you have multiple flasks like this, you just need to make sure that you do a Boyle's Law problem first, okay? You have about 3 or 4 of these on your homework. We're not ready for our homework yet. All right. I'm going to go back to our notes. We got to finish. We still have a little bit more with Dalton's Law still left to do. 12, 13. All right, you're also going to notice that I posted something. I worked these examples out. I have posted a thing on the stream, okay? It says a vapor pressure of water table, okay? Vapor pressure correction. So if gas is collected over water, the gas becomes saturated with water vapor. We know this. That's why when you boil water, this is what happens, okay? The total pressure of the gas collected will be equal to the total pressure of the gas and the pressure of the water vapor. So the total pressure is equal to the pressure of the gas and the water vapor. So this is a Dalton's Law equation. P total equals P gas plus P water vapor. Okay? P total equals P gas plus P water vapor. A listing of the different vapor pressures can be found in table A8 on page 899. I've also posted a copy of it on the Google Classroom stream, okay? So if you go look at that on that stream, Zaire is pulling it up right now. It tells you that, well, maybe he'll pull his up now. It tells you that, let me find my stream. Yeah, it looks like this. It tells you that at 0 degrees Celsius, the pressure in kPa is the P vapor is 0.060 kPa. Yeah, I think your book uses millimeter mercury. Some places use ATM. You just might have to convert some things in there, okay? So however you want to do it. So you'll use this table. Anytime you hear a water vapor, that's kind of code word for, hey, we need to look at this chart, okay? So big thing here is P total equals P gas plus P water vapor. Evaporation, okay, this is just definitions. Things evaporate when they have enough energy to break free of the surface to become liquid to become a gas, okay? Surface liquid become a gas. This is why, can you boil faster with the lid on or off? On, because you're keeping more pressure on it, okay? You're keeping more pressure on it. Important notes about vapor pressure is temperature dependent. The higher the temperature, the higher the vapor pressure. Does not depend on the size of the container. At boiling point, the vapor pressure equals atmospheric pressure. Okay, this is why we talked about earlier in the unit that if you want to go cook like things like at a high altitude, like I know that scalloped potatoes have your instructions to cook at normal and then instructions to cook at high altitude. Okay, because things boil at a lower temperature at higher altitude. So examples. Let me come back to my examples. Let's go back to our paint. So 2 examples of these. One kind of simpler, like the other thing, and then one a little bit more difficult. All right. So there is our first question. Give you a chance to write it. I'm looking for the partial pressure. So I know my equation, same equation I just used. We know that P total, and this is the same thing as the first one we did, equals P gas plus P vapor. Okay, That's my equation. The same thing as I did a while ago. P total equals P CO2 plus PO2 plus C SO2. So I'm looking for partial pressure, aren't I? So I know my total pressure then, don't I? My total pressure is what? 748 equals, I'm looking for the dry gas. I'm looking for the P of the gas. So that's my X. Plus, what is my P of my vapor pressure? So what she did is she went and looked at that table and she went to 35 degrees Celsius and she saw that it is 5.6 kPa. Okay, so now I need to convert from kPa to millimeters mercury. So 5.6 kPa over 1 times. So really you're dividing by 101.325 and then multiply by 760. And that answer is 42, I think. It's 42. So this pressure is 42 millimeters mercury. I got that from converting from 5.6 kPa to millimeters mercury. So what's my P gas? 706. And what units would it be in? Millimeters mercury. I could have answered this question. I could have converted this to kPa. I could have converted both to atmospheres. It doesn't matter what unit was in, so long as they're in the same units, okay? All right, last question, and then we're gonna have to kind of speed. I'm probably gonna not give you time to write this one. If I want to go back and work this one out, okay? Because I don't want to run out of time. So, I mean, I probably would, but I don't think you're gonna have time, okay? So, oh, dummy. Almost time to go, yep. So, last question, we can work through it together. It tells you that a sample of oxygen collected over water. The wet gas has a volume of 7.28 liters with a temperature of 25 degrees Celsius and a pressure of 1.23 atmospheres. What is the volume of the pressure? What's the volume of gas? Should say what's the volume of gas at STP? What's the volume of gas at STP? So I'm giving two volumes, aren't I? I mean, I'm giving one volume, looking for another volume. So this is both questions combined. This is a P1 V1 T1 and a P2 V2 T2. What is P1? What is P1? 1.23 ATM. What is V1? What? 7.28. And T1 being 298. Got to convert that to Kelvin. Now, what is the volume of the pressure? So what's the volume at, so I can't use standard pressure here, okay? I cannot use standard pressure. So what I need to do is, I know that my total pressure, I'm only looking for the pressure of the gas, okay? The wet gas. I'm looking for the pressure of the gas. My total pressure is 1 atmosphere. So P total equals 1 ATM. But I need my P gas. But I also know my P vapor. So I go and I look up the P vapor at 273 Kelvin. So I go back to that chart that I posted. And I know that my T2 is 273.15. I go back and I find my pressure. I go back and find my pressure, and the pressure at 273 Kelvin is 0.6 kPa. So I have to convert from 0.6 kPa to atmospheres. So 0.6 divided by 101.325. And so my P vapor is equal to 0.0059. So now I know 1 minus 0.0059 is 0.99. So my P gas is 0.99. That now goes into my P2 because we are talking only about the wet gas. If it was the total gas, this did not say wet, I would have just used P2 as 1.0 ATM. So now I'm ready to solve this out. 1.23 times 7.28, 298 equals 0.99 times X over 273.15. And my answer is equal to 7.99 liters.
Where's my work for that quiz?
Sit it right there.
I'm being stupid.